Okay, here's something that'll mess with your brain. Right now, there are particles in a lab around the world that are having conversations with their partners across the universe. Instantly. This weird phenomenon made Albert Einstein so mad that he basically spent the rest of his career arguing with the universe about it, and lost. Today, we're diving deep into quantum entanglement. And fair warning, this episode is going to get real sciencey. We're talking about the physics behind the most mind-bending relationship in existence. Google is already making billions off something that we literally can't explain. Buckle up, because we're about to explore how the universe might be way weirder than any of us actually thought. You know how sometimes you'll think about someone, think about texting them, and you pick up your phone and that exact moment they text you. That's weird, right? Well, quantum entanglement makes that look like child's play. We're talking about particles that somehow know what their partner is doing from literally across the universe, instantly. Albert Einstein discovered this back in 1935, and it absolutely broke his brain. The man who figured out relativity rewrote physics. He looked at quantum entanglement and basically said, nope, universe doesn't work that way. He called it spooky action at a distance, and he spent the rest of his career trying to prove it was wrong. Einstein wasn't having a bad science day. He was genuinely disturbed by what this meant. See, according to the theory of relativity, nothing travels faster than light. Nothing. But quantum entanglement seemed to show particles communicating instantaneously across any distance. Einstein thought there had to be some hidden mechanism we're missing, like the particles were secretly coordinating their behavior beforehand. He published this famous paper with two other physicists, Podolsky and Rosen, essentially arguing that quantum mechanics was incomplete. They called it the EPR paradox, which sounds way cooler than what it actually is. Einstein was convinced that God does not play dice with the universe, meaning everything should follow predictable rules. Here's the thing, though. Einstein was wrong about this one. The universe absolutely plays dice, and apparently, it's really good at it. Modern experiments have proven that quantum entanglement is completely real, and it works exactly as weirdly as the original theories predicted. So we have this phenomenon that works perfectly in our labs, that we're already using in technology, but that still makes absolutely no sense according to our understanding of how reality should function. It's like having a car that runs great, but nobody can explain why the engine works. Creating entanglement particles is surprisingly straightforward, which makes the whole thing even more bizarre. You can take a laser and split a single photon into two particles that become quantum twins. Or you can smash particles together in an accelerator, and sometimes they'll produce entanglement pairs. Once you have these pairs, they exhibit what scientists call superposition. This means they exist in all possible states simultaneously until someone measures them. Think of it like a coin that's spinning in the air. It's both heads and tails until it lands. Except these quantum coins stay in that spinning state indefinitely. The truly wild part happens when you measure one of the entangled particles. The moment you do, both particles instantly snap into definite opposite states. If you measure yours as spin up, its partner immediately becomes spin down, no matter how far away it is. We're talking about distances of hundreds of miles in current experiments, but theoretically, it could work across galaxies. In 1964, physicist John Bell created a mathematical theorem proving that this correlation couldn't be explained by any hidden variables or secret communication between the particles. Then in the 1980s, Alan Aspect did a series of experiments that definitely showed Bell was right. The particles weren't secretly coordinating, they were genuinely connected in a way that defied classical physics. This revelation spawned an entire field of quantum technology. Companies like IBM and Google are building quantum computers that use entangled particles to perform calculations exponentially faster than regular computers. Quantum cryptography uses entangled particles to create unbreakable codes because any attempt to intercept the message would destroy the entanglement. We've also achieved something called quantum teleportation, which sounds way more exciting than it actually is. We're not beaming people around like Star Trek. We're transferring the quantum state of one particle to another. The information gets teleported, not the particle itself. The practical applications keep expanding. Enhanced medical imaging, more precise GPS systems, revolutionary computing power, all because we learned to harness this phenomenon that Einstein thought was impossible. Now, here's where things get properly mind-bending. We can use quantum entanglement, but we have absolutely no idea how it actually works. It's like having a magic wand that consistently produces magic, but having no clue what magic even is. The fundamental question is, how do these particles communicate faster than light without violating Einstein's speed limit? Some physicists think this information isn't actually traveling between the particles. Instead, they theorize that the measurement of one particle somehow affects the fabric of reality itself, instantly influencing its partner. There are several competing interpretations of what's happening. The Copenhagen interpretation says that the act of observation literally creates reality. The particles don't have definite properties until someone measures them. The many worlds interpretation suggests that all possible measurement outcomes occur simultaneously in parallel universes. Another theory proposes that there's a hidden outer guiding principle behavior that we can't detect. Recent experiments have tried to remove human consciousness from the equation entirely, using automated systems to make measurements. The entanglement persists regardless, which rules out some of the more mystical explanations but doesn't solve the fundamental mystery itself. Scientists have successfully entangled particles across continents using satellites and fiber optic cables. They've even entangled increasingly large objects, individual molecules, small crystals, tiny diamonds. Each success pushes the boundaries of what we thought was possible. But entanglement is fragile. Environmental interference, heat, vibrations, almost anything can break the quantum connection. This decoherence problem is why we don't see quantum effects in everyday life, even though the same rules apply to everything in the universe. The scale question fascinates researchers. If we can entangle molecules, could we eventually entangle larger objects? What about living things? Some scientists have found evidence of quantum effects in biological systems, photosynthesis in plants, navigation in migratory birds, possibly even in human brains. This connects to one of the most contentious debates in physics. Does consciousness play a role in quantum mechanics? Some physicists argue that consciousness is required to collapse the wave function, while others consider this pseudoscientific nonsense. The measurement problem remains unsolved after nearly a century of investigation. The past few years have brought discoveries that make quantum entanglement even stranger than we thought. Scientists have observed what they're calling ghost-like particles that briefly emerge from the quantum vacuum during entanglement events. These virtual particles become temporarily real, suggesting that empty space is far from empty. Researchers have achieved room temperature entanglement, overcoming previous limitations that required near absolute zero conditions. This breakthrough makes quantum technology far more practical for everyday applications. Some experiments have produced results that seem to violate our understanding of causality itself. In delayed choice experiments, scientists can apparently influence the past behavior of particles by making measurements in the present. These results suggest that cause and effect might not work in the way that we think they do at the quantum level. Even more perplexing are experiments showing retroactive entanglement, particles becoming entangled backward in time. If confirmed, this could revolutionize our understanding of time itself. Scientists have also succeeded in entangling particles that have never directly interacted, using a process called entanglement swapping. They can create quantum connections between particles that have never been in the same place at the same time. Current research is pushing into biological systems. Experiments with chlorophyll molecules show quantum coherence lasting much longer than classical physics predicts. Some researchers are investigating whether quantum entanglement plays a role in consciousness, though this remains highly speculative. Major governments and tech companies are pouring billions into quantum research. racing to build practical quantum computers and communication networks. The European Union is constructing a quantum internet connecting major cities. China has launched quantum communication satellites. The U.S. has designated quantum information science as a national priority. Within the next decade, we'll likely see limited quantum computers solving scientific problems much faster than conventional machines. Within 20 to 50 years, quantum technology could transform computing, communication, and our understanding of reality itself. But the fundamental questions remain unanswered. Will we ever truly understand why entanglement works? Could it be evidence of other dimensions or parallel universes? Some speculate that entanglement might be the key to understanding dark matter and dark energy, the mysterious forces that make up most of our universe. The consciousness question persists. If quantum mechanics influences biological processes, and quantum mechanics seems to involve the act of observation, what does this mean for free will and the nature of awareness? Maybe most intriguingly, some theories suggest that space and time themselves emerge from quantum entanglement. In this view, the universe is fundamentally made of information, and what we perceive as physical reality is the result of quantum connections between particles. Nearly a century after Einstein objected to spooky action at a distance, quantum entanglement remains our universe's most elegant paradox. We've learned to harness its power, but its essence continues to elude our comprehension. It works flawlessly in practice, while remaining theoretically inexplicable. Maybe that's the most profound lesson quantum entanglement teaches us. The universe is under no obligation to make sense to us. Sometimes the most important truths are the ones that force us to expand our definition of what is possible.